So for this lab makeup, we're going to be doing the gas laws. And we're going to use the gas laws very specifically to find out what the molecular weight of a gas is. So we're going to find the molecular weight. So the analogy I like to use is molarity. So how do we find the molarity of something? Well, we define the molarity as the moles over liters. And so all we have to do is find the moles, and find liters, and divide. So we find the moles, find the liters, and we divide. Yeah. It's pretty simple. Well, we can do something similar for molecular weight. With molecular weight is grams per mole. Usually 1 mole, and so we define the molecular weight as the mass of 1 mole. But we can also use that in a similar fashion as the ratio that we did for molarity. It is grams per mole. And so if we know the grams and we know the moles, we can figure this out. And so that's exactly what we're going to do. We're going to use the universal gas law, the ideal gas law, PV equals nRT, to find the number of moles. So if we know the number of moles, that's the beautiful thing about the gas law. The gas law is perfect for finding the number of moles. So we would just have to rearrange this as such and plug in the requisite values, and we would be able to calculate the number of moles. And that's what we're going to do. We're going to go into, well, that's what we did, actually. You missed it. We're going to go in the lab, and we're going to measure the pressure, and the temperature, and the volume of a gas. Easy. The thing is, this needs to be in atmospheres. This needs to be in Kelvin, and this needs to be in liters. And so, we have recorded some data for this lab. And what we've done is we've taken Erlenmeyer flask, and we filled it with gas. In this case, this gas is CO2. And so we fill it with CO2, we fill it completely to the top with CO2, and we then weigh it. So from the pressure inside the container, and the temperature inside the container, and the volume inside the container, we can calculate the number of moles inside that container. All right. So what you'll see is that this is exactly what we do. We have the pressure in millimeters of mercury, convert that into atmospheres. We have the temperature in degrees centigrade, convert that into Kelvin. And then we have the volume in the flask, which we'll have to convert into liters. Now those 3 quantities we combine, and the gas constant. The pressure, volume, and temperature together allow us to calculate the moles of gas, which will be the same, these 2 values here. So we will plug it into our equation, rearrange and solve, and calculate the number of moles of gas. Now, that's the first part. Now, the actual practical side of this is figuring out the mass inside the container. The problem is, how do we normally find the mass of something? Well, we do it by subtraction. And so we have this flask with a stopper in it, and we're going to weigh it. But the problem is this thing isn't empty. It's filled with air. So somehow we have to subtract out the air. So the way we do that is indirectly. It turns out that if we know the volume of the container, we can use the density of air, how much air is actually in there, from the density. So if we know the volume, and we can combine it with the density to find the mass of air. Now, in about a liter of air, it's about a gram. So, but we're not using a liter, we're using a lot smaller volume. So we would expect it to be substantially smaller. Right? And so we can calculate this. And so using the density of air here and the volume here, we can figure out the mass of air. So if we know the original mass and the mass of the air, and we subtract those two out, that will be just the mass of the empty flask. Well, once we know that, if we know the mass with the CO2 minus the mass of the empty, then we can figure out what the mass of CO2 is. So once we have that mass of CO2 and the moles, we take the mass divided by the moles, and we should be able to determine this amount of the CO2, the molecular weight of CO2. Now we know that the actual, so we'll experimentally determine our molecular weight. Well, we know what its actual value is. So if we subtract it from the actual and we divide it by the actual times 100, that will equal our percent error. Right? So you take our experimental value and subtract it from the actual, which we know is 44 grams per mole, and then divide it by the actual to see how far we are, and we can see how close we get to our pair. So that should be enough information to solve this problem.